Retarded, because that's a bad thing to say, huh? Phil could have done because hey, we're all retarded here, right? We
Yeah.
Okay. Boy. Anyway, so we're just going over examples that are your text because those are the easiest for you to go back and reference. Some of these, we'll definitely test you a little bit on these when we get into your homeworks. But real quick, look at this particular reaction. We'll say that we've got H2 gas plus solid iodine going on to form hydrogen iodide. Two of those. What's our equilibrium constant for this reaction look like?
2H.
Huh? For pressures, the K sub P. What's K sub P look like for this guy?
Pressure of hydrogen iodide squared over pressure of hydrogen gas.
Okay. So it's P of HI, and you said because it had a coefficient of 2 in front of it, that we were going to square that guy, right? And what else we got in there?
H2 and I2. Plus H2.
But you said it was pH 2. The first power.
Oh,
yeah.
Yep.
Right? Because this guy's a solid, so that doesn't end up showing up in our equilibrium expression. Yeah? So what we're going to do is we're going to take a moment and we're going to recast this expression in terms of the partial pressures of these species. Remember, this is all gas-phase species. We're going to recast this expression in terms of the partial pressures of the species and their mole fractions. So if you've got a volume that's made up of just HI and H2, so a gas-phase volume, just HI and H2, we know that PHI is equal to the total pressure times the mole fraction of HI. Yeah? And similarly, P of H2 is equal to the total pressure times the mole fraction of H2, which you can call it 1 minus the mole fraction of HI if those are the only two species in solution. We're not going to go that far today. We're just going to take a quick glance at what this looks like. So we swap in these values, and you get that KEQ is equal to the mole fraction of HI times pressure total squared over the mole fraction of H2 times pressure total. Simplifying, this just ends up being the mole fraction of HI squared over the mole fraction of H2 times pressure total. We get pressure total squared in the numerator. We get 1 factor of pressure total in the denominator. So overall, we've got just pressure total to the first power in our answer. Now I told you that earlier that because we were looking at K expressions that were basically determined by whatever the standard pressure delta G of the reaction was, I told you that those Ks aren't going to be subject to changes in pressure, right? The K is going to be constant even if you do change the actual pressures that the reactions are occurring in. So if this has to stay constant, and it has one value at some initial pressure, what is going to happen in terms of the mole fractions of HI and mole fractions of H2 if we all of a sudden put this at a new total pressure? We squeeze the reaction vessel and crush its volume to half of its initial volume. What's going to happen if this increases in order for the total product to stay equal to the same number?
Mole fraction, the ratio will have to decrease.
Yeah, for this to stay constant, if pressure increases, then your mole fraction of HI is going to have to decrease, and your mole fraction of H2 is going to have to increase. And so if you increase the pressure, you drive the system in the direction of the lesser number of moles of gas, right? And similarly, in this particular system, if you decrease the pressure, you're going to drive the reaction in the forward direction towards having more moles of gas. And that's basically what we learned to predict from Le Chatelier's principle. When you've got gas-phase species and you change the pressure, the total pressure, you'll push the reaction to whatever direction minimizes the change. Right? If it was an increase in pressure, you're going to drive it towards the direction or the side with fewer gas-phase species. If it's a decrease in pressure, you're going to drive it towards the side with more gas-phase species. Incidentally, your book makes an error here. I'm going to read something to you. This is on page 180. It says, for K to remain constant as the pressure increases, the ratio of mole fractions must decrease, right? And that's, that I believe. But then they say, implying that the proportion of HI in the mixture must increase. They get it right and then they get it wrong right in the same sentence. So that made me bang my head against the wall. I had to talk to Jesus about it. I just figured I'd let you guys know right away. I didn't really talk to Jesus about it. Yeah, a little confusing. Just what do you think?
Maybe there's a kid with name Peter.
I had one of those. That was anyway. You guys seen that? You seen that comic where in the one side they got the hoity-toity aristocratic family sitting down to their meal, and they're all sitting there saying, "Thank you, Jesus, for the food before us." And the next screen over, they got the Latino kid out in the field, and he's picking his vegetables, and he says, "De nada." The kid in my class, his name was Jesus. That was his favorite comic. All right. So you're going to have homework problems that ask you to do that same manipulation. It might not be that we've got this exact kind of arrangement. Depending on, you can imagine, depending on whether or not your reactants or products have more gas-phase species, you'll end up with pressure total either showing up in the numerator or denominator. In our system, we had more gas-phase species than products, and so the pressure total showed up in the numerator of our expression. If we had more gas-phase species in the reactants, then the pressure total is going to show up in the denominator of the expression. So just because pressure total showed up in the numerator here, don't expect that to mean that it's going to show up in the numerator in your homework problems or exam problems. All right? So you're going to have to do something along that line. Tom,
10 minutes.
10 minutes? All right. So I'll just show you your homework assignment, what is going to be your homework assignment.
I'm not doing anything, I'm just listening to people.
Better than listening
I don't know, I think
Good school.
Well, I mean, UCLA, I guess.
That person,
She was so wanted that.
So I might have already shown this to you. This is gonna be your homework to take home over the weekend. Yeah, I already kind of showed this to you a little bit, I think, in preparation for the last exam. But we basically give you the equation for the synthesis of ammonia, the same reaction we just looked at. And in problem number 1, I just give you some initial conditions and ask you to calculate what delta G of the reaction is for those initial conditions. And for that, you're just going to plug in delta G is delta G naught plus RT natural log of Q, and you'll have to, draw out Q based on the partial pressures and the coefficients in the balanced equation, and tell me what direction or what the spontaneous direction of the reaction is. For this guy here, I just asked you to kind of look at the reaction in terms of the volumes and the entropies, and to predict how this reaction is going to respond to changes in temperature or changes in pressure, right? So you should be able to look at the relative volumes of the products and reactants and the relative entropies of the products and reactants, and predict from the equation how that thing is going to respond to those changes in condition. What's that? Oh, for the reaction to happen? I think that number 3 is asking you to use the Van Hoff equation that we just kind of quickly derived for you. Is that equation 7.15? Yeah, 7.15 is the Van Hoff equation. So problem number 3, you're just being asked to use the Van Hoff equation. Number 4 just asks you to explain why endothermic and exothermic reactions behave the way they do when it comes to a temperature change. We just had that conversation. That shouldn't be that difficult. And
Professor, are you going to have working hours next?
office hours? Yeah. And then number 5, this whole homework set is based on the same reaction. Number 5 is just asking you to write out the K of pressures, K sub P, for ammonia, and then look at that and based on that, answer how the system is going to respond to a change in pressure, right? So for problem number 5, you're just going to be doing this little bit of logic here, except with the ammonia reaction, and you're going to be telling me how that reaction is going to change or how it's going to respond when you alter the pressure. Yeah, you can do that. Okay. Um, 7 asked you to determine whether or not these species are endergonic or exergonic. We haven't talked about that piece of vocabulary. It's in your text. You can read the section of the text. Endergonic basically means that the Gibbs free energy of the actual molecule is higher than the Gibbs free energy of the atoms from which it's composed of. So, so you have to go up in the Gibbs free energy, which means that the actual molecules are are relatively unstable compared to their elemental precursors. Exergonic means that you've got negative delta G of formation for a species, and so the actual molecule form is more stable than the elemental precursors. So to answer number 7, you're just going to go calculate delta G naught, or you're going to go look up delta G naught formation for those species, glucose, methylamine, octane, and ethanol, and just based on its sign, you're going to tell me whether or not that species is stable or unstable compared to its elemental precursors. Right? I don't know what the others read, but it's time to get out of here. What's that?
Metformin would be the only one from that list.
What, you're guessing?
I'll try to, maybe loud, but I can't.
You're better than me.
Well, because glucose takes a lot of energy. Octane takes a lot of energy. Methanol takes a lot of energy. Metformin.
You're right. I'll be impressed.
No, actually, what's
Oh my eye. Is it really big? I don't know what it is. It's just like it started hurting and like the first thing. I think I'm done. Yeah.
But then, yeah. Because I'm gonna go get a
Have fun. You guys are crawling around in those things.
too soon. Because I don't say no.
Yeah.
It's not the surface.
I'll
There's two different generations. When you say no, the character.
from my Gen Ed class.
Yeah, I put air.
So they're all coming to office hours.
They're all I don't know, it was huge. It's like, it was 9 years here, it's been for over.
Hope you get better. Bye.
It'll happen after break. Yeah, after break, I'll hopefully over break, I'll get all of the rest of my lectures written. Don't be worried about that, so be ready for after break. It's all on Monday. Scan it.
Yeah, it's going around.
Oh, that's fine.
Yeah, really bad.
Yeah, there's morning bubbles.
No, it's the one I just showed you, and I'll put it on mine.
How are you?